We use electricity in our daily life for various applications. For example, to light bulbs, to heat an electric iron, and operate refrigerators and air conditioners. All these applications require different amounts of current. Find the most efficient way to get the proper.
Let's begin by looking at how a simple circuit allows a light bulb to light. A circuit is a route through which electrical current can flow. In our example, electrons flow from the negative side of a D-cell battery to a conducting material on the base of the bulb. From there, the electrons flow up a wire that is inside the bulb and across the filament, which is the part of the bulb that actually lights. When the electrons go through the filament, some of the electrical energy is changed to heat and light energy. The electrons continue down another small wire inside the bulb to another conductor on the base of the bulb. The electrons finally make their way to the positive side of the battery. There would not be a complete circuit if the electrons did not travel to the positive side of the battery, and the bulb would not light. When there is an unbroken path on which electrons flow, as in this example, it is called a complete circuit. The unbroken path that the electrons follow is called a closed circuit, because electricity will only flow on an unbroken path. The light bulb will not light unless there is a closed circuit. Now look closely at the light bulb, and you'll notice that there is an insulator between the conductor that leads up to the filament and the conductor that leads away from the filament. Remember that the atoms of conductors easily accept and pass on electrons. The atoms of insulators do not. As we discussed in the first section of the lesson, electrons will not easily pass through insulating material that surrounds a wire. If an insulator did not surround a wire carrying a current, it is possible for the electron flow to get directed to another conductor that comes into contact with the circuit. Electricity will follow the path of least resistance. If the electrons take a path short of the complete circuit, it is called a short circuit.
Today, we will discuss about conventional and electron current flow. Consider a dry cell, as shown here. This cell has one positive and one negative terminal. The difference of potential between these two terminals is measured in volt. And this difference is due to an excess of electrons at the negative terminal compared to the positive terminal. If we connect a wire across these two terminals, the potential difference causes an electric current to flow in the circuit. This current is nothing but a flow of electrons that come out from negative terminal, move along the wire, and enter the cell by the positive terminal. However, before invention of this electron theory of current flow, the scientists of the 17th century arbitrarily decided that the electric current flows from positive potential to negative potential. This is so-called conventional flow of current. Till today, this is accepted as direction of electric current flow. Hope you understand. Thank you.
Here we have a selection of various electrical components, and all of these you need to know about for the course. And what I'd like to do is just show you the circuit symbols and what stands for what. So here we have a cell or a battery. Now a cell is an individual unit, just like a prison cell is, or maybe the cell inside the human body is just the smallest unit. Now what we can do is we can add individual cells together, and when you have a number of them together, what we have is a battery. Just like you have a battery of chickens is many chickens, or a battery of artillery guns is a battery, that's just many things together. You also need to know about a filament lamp. Now a filament lamp tends to have the symbol just like this. It's just a cross inside a circle. So that's fairly straightforward, all GCSEs so far. We also have a component called a resistor. Now a resistor, these often have different colour bands that tell you the size of the resistor. It's often quite hard to print the information you need. And if you look at this, it's like this kind of oblong on the block. So this symbol here is our resistor. So just that rectangle, which looks a bit like the resistor that we have. But there are other kinds of resistors. We have some resistors that change their value. And because they change the value, we put an arrow to show that it can increase or decrease. We also have a resistor like the one here. Now this one here basically has some sensitive strips on the top, and what these do is they change the resistance dependent upon the light intensity. So this one here, and it's circular as well, this one here is our light dependent resistor. So this light dependent resistor has rays of light that come into it, and that changes its resistance with the light intensity. We also have a kind of resistor called a thermistor. What I have here is a negative temperature coefficient thermistor, and basically this bit at the top, when it heats up or changes temperature, the overall resistance changes, and the symbol looks a bit like this kind of sort of a hockey stick or something like that over this resistor here. And this one here is a negative temperature coefficient, and I'll talk about more of that in one of my later videos. We also have a thing that is basically our one-way valve, and what this does is it lets the current go through in one direction, but anything going the other direction is stopped. And this is what we call a diode. So the diode actually looks a bit like a resistor, but it's a different component. Now there's different ways of drawing a diode. Sometimes it just looks like I've drawn here. Sometimes we put a circle around it. And there's also a kind of diode that emits light. And the ones that give out light are called the light emitting diodes. And these are big news. This one here is just a kind of a thing that you can get from IKEA. And the actual LEDs, because I actually broke the top of this one, are these little orange bits down here. And these light up and give out a fantastic amount of light. These things here are going to be the future. They're going to get a lot cheaper, and very soon they're going to start to replace every single other light in your house. Now you need to measure the current in bits of the circuit, and this is where we can use an ammeter. This one here says A in a massive letter, so you know exactly what it is. And going alongside to measure the current, we can also measure the potential difference across components. And we do that using a voltmeter. And that's pretty much it. These are the things that you need to know, and with these basic components you can then start to kind of construct circuits in parallel, in series, and also these potential divider circuits, which is where it gets a bit more tricky. But you must be able to know what all of these are, identify them, and draw them appropriately.
Insulators, conductors and semiconductors. Insulators, the substances which do not allow current to flow through them with ease, are called insulators. In general, they do not have free electrons. Cotton, rubber, plastic, wood, paper, glass, air, leather and pure water are examples of insulators. Conductors, the substances which allow current to flow through them with ease, are called conductors. They have a large number of free electrons and ions. All metals such as copper, silver, iron and also impure water are examples of conductors of electricity. Semiconductors. Semiconductors are those materials which allow a very small current to flow through them when a source of large potential difference is connected across their ends. Example: germanium, silicon. Simon Ohm in 1826. According to Ohm's law, the electric current flowing through a conductor is directly proportional to the potential difference across its ends, provided the physical conditions such as temperature, pressure, etc. of the conductor remain the same. Principle: if I is the current flowing through the conductor and V is the potential difference across its ends, then according to Ohm's law, V is equal to Ri, where R is the constant of proportionality. It is known as resistance of the conductor. Or V by I is equal to R. Knowing the length L and radius R of a graph of potential difference versus current. Materials required: battery eliminator, ammeter, voltmeter, a resistance wire, rheostat, one-way key. Procedure: arrange the required materials according to the circuit diagram. The positive terminal of the battery is connected to the positive terminal of the voltmeter, which is connected in series with the ammeter. Through a key, the connection can be extended to the upper terminal of the rheostat, whose lower terminal is connected to the negative terminal of the battery. The given resistor must be connected in parallel to the voltmeter. Determine the least count of voltmeter and ammeter and also note the zero error. To check the connections, insert the key K, then slide the rheostat contact and see whether the ammeter and voltmeter are working properly. By adjusting the sliding contact of the rheostat, note down the value of the potential difference V across the resistor from the voltmeter and current I from the ammeter. Repeat the experiment by changing the rheostat slider position. In each case, V by I is calculated, which gives a resistance R of the resistor, and it is found as a constant. Cut the resistance wire at the points where it leaves the terminals, stretch it and find its length by the meter scale. V along the y-axis. The graph is a straight line. This also verifies Ohm's law. The slope of the graph will give the resistance of the wire. Note the values of OB and AB, then calculate the value of R as AB by OB, which gives the value of unknown resistance.